What do I start again? In this talk, I want to take you through how and why the machine was developed, and who by, a little bit about how it worked, and then how it was used. Let's do it this way.
Click on the, somewhere on the
Yeah.
and then click on the
Right.
there.
Magic. So this is the order I'll be doing it in. I want to tell you a little bit about where it came from and how it fitted in with other things going on. What the post office did and why they did it. Look at how it worked, and particularly this thing called optimal programming, which meant that you would try and make the best use of the machine you possibly could by exercising the greatest control you could. Then look at what it looked like in RRE in Malvern and how they used it. Then there'll be a little bit of a catch up on what was happening with mainstream ACE at the time. Whoops. So a useful place to start is this classic model of the evolution of ICL. Really, I'm focusing on these four developments because they illustrated the four main options for storage at the time. The Birkbeck machine relied on magnetic drum for its main storage. The Manchester machine excited phosphor dots on a cathode ray tube, and Pilot ACE and EDSAC, which were concerned with magnetic delay lines. And the development of these three machines collides with each other occasionally. Dollis Hill doesn't appear on there. It was a post office research station. It was built in the 1930s and very quickly generated a worldwide reputation. And at that place, we have these four researchers: Tommy Flowers, Sid Broadhurst, Alan Coombs, and William Chandler. They are the team that breathed life into Colossus, and obviously worked with the guys at Bletchley Park, so that when Alan Turing, at the end of the war, went from Bletchley Park to NPL to work in the mathematics department and to build his automatic computing engine, he wanted to engage them as his hardware development team. Similarly, Newman went to Manchester to a chair in maths, and at Manchester he came across Williams, who had been working at TRE, where he developed, in conjunction with Tom Kilburn, the CRT method of storage. In late 1946, the professor of physics at Manchester, Blackett, who already knew Williams, and Williams was an ex-Manchester man, recruited him. He was interviewed by both both Blackett and Newman, and he went across, taking Kilburn with him as a PhD student and Jeff Tutel with him, and Tutel would eventually end up working at Ferranti. So that was the core of the Manchester team. Wilkes was also at TRE, having initially worked at the mathematical laboratory in Cambridge, and at the end of the war he went back to Cambridge. There he met an astrophysics student doing his PhD at the Cavendish, Thomas Gold. Thomas Gold, during the war, had worked on mercury delay lines. and he was able to tell Wilkes exactly how to make a mercury delay line work, because they were temperamental beasts. And he also introduced Wilkes to William Rennick, who would work with Wilkes on making that technology work for EDSAC, and who published a paper with him in 1948, which everyone else who was trying to get a delay line to work made use of. That leaves us back with the post office team. 4 of them, except Broadhurst, never worked on ACE. Flowers was seen as the main man, but unfortunately the post office was under a lot of pressure to actually restore the telecommunications network in the UK to a better standard, it having fallen behind in both technology and due to war damage. So we're left with Coombs and Chandler on the project, and that meant it suffered somewhat. So this is a rough timeline. The post office had their first delay lines in a demonstrable state by the end of March 46. Now, bearing in mind, they didn't have a lot of experience in delay lines. Once they got them working, it took them a long time to get them stable. So much so that the guys at NPL started to get worried, and management started talking to other people, notably TRE and Wilkes. TRE looked quite promising, although there were likely to need substantial changes in moving from a CRT to a delay line architecture. But then Williams left and went to Manchester, and there was a view that perhaps Williams could still help them and sign a contract with them, but he never did because he was too busy and really wanted to build his own machine. Wilkes, on the other hand, produced a design which he submitted into NPL, and the guys looked at it and passed it on to Turing. Unfortunately, Turing and Wilkes thought very differently about machines. Turing's approach was, what you want is a really fast and reliable machine, and the way you get that is you simplify the electronics, even if it means that you make life a little more difficult for the programmers. Wilkes, on the other hand, was very keen to make the hardware sophisticated enough to simplify life for the programmers. Ultimately, at the end of that period, by the sort of March 47, it was clear that the way ahead was working with neither, and NPL started looking at building their own capability. That becomes more of a reality when Turing went off to the States, and about the only thing that really impressed him about how the Americans worked was that they made pretty sure that their mathematicians and their engineers were co-located so that communication between them was much easier. This is clearly not very easy to do between Teddington and Dollis Hill. So a decision was taken to grow NPL's own capabilities. Also, while Turing was going one way over the Atlantic, a guy called Harry Husky was coming the other way. He'd worked on ENIAC, and he worked with Jim Wilkinson, who was one of Turing's men, on building of the simplest version of ACE he could, and that was called the test assembly. Round about March 47, the team at NPL, sorry, I'll start that bit again. Round about March 47, it was decided that NPL will make use of electronics expertise in their radio division to build a team to attack ACE. That was done. It was headed up by a guy called Thomas, but because of the internal politics, getting the right people together meant the whole thing labored on until August. Come August, Womersley, who was Alan Turing's boss, said to Charles Darwin, his boss, don't you think we ought to be having a conversation with the post office now that we've gone away? Oh, and by the way, do you also know that since about 1946, they've been talking to the Ministry of Supply, who were the equivalent of the MOD in those days, on the building of a new machine. And that would be the Ministry of Supply Automatic Integrator or calculator or computer. Why were they interested in doing that? Well, the whole defense world had been somewhat shaken by the invention of the V2 and the atomic bomb. And also from their own experiences of radar and other things, they discovered that the defense business was getting increasingly technical. The more technical you get, the more data you generate. And if you've generated data, you've got to do something with it. That takes mathematicians and machines, and soon you run out of mathematicians and machines. So let's think about a computer. And that's what they did. So in 1946, the post office were a bit hesitant to go forward, but Coombs persuaded them that it was the right thing to do, and they took on Mosaic, which would be to a slightly different iteration of the ACE architecture to what would eventually become Pilot ACE. So immediately after that, September, Turing went off on sabbatical. The new team was formed, and one of the things Thomas did was he stopped work on the test assembly. By the end of 47, Husky had gone back to America. And in 1948, Colebrook resigned, went to work for Unilever. Colebrook, Thomas, and his place was taken by a chap called Francis Colebrook, who immediately set the ACE project on a firmer course, measuring on Pilot ACE, reutilizing as much as possible of the test assembly with a long-term view of building a big machine. And this is how this pans out as a family of machines. So if we start with logical design 5, this was the thing that test assembly was majoring on, and that was what is known as the 3-address machine. So you could only have one source address, one destination address, and a next instruction address. So ACE didn't use a program counter. So it also didn't allow you to specify a function. So the question is, how on earth do you do anything meaningful with it? Well, it's all in the way you express register usage as you build your code. So for instance, an instruction that had a source address of TS15 and a destination of TS16 would merely take what you had in 15, put it into 16. If, however, you specified a destination of TS17 instead, then the contents of TS15 will be added to the contents already in TS16 to give a result. As you can see, it's a little bit contorted. Logical design 7, which was another of Turing's designs, was a 4-address machine. This allowed you to specify not only a second source operand, but also a function code. So everything was much clearer, and there was no special use of addresses within the normal address range. There were some special addresses, as we'll see later. Just to round that off, logical address 7 was an iteration that took place at MPL after Turing had left, and that was the basis of full ACE, and it was also a 4-address machine. Pilot ACE, Colebrook got English Electric interested in working with Pilot ACE, and they were impressed enough that in 1953 they decided to develop a commercial version called Juice. There were about 33 of those sold worldwide. Husky in the States also used the same architecture, but used magnetic drum to emulate the delay lines in the form of the Bendix G15, of which 400 were sold. The Packard Bell was a derivative of that, which was all transistors, made in the 1960s. And the EMI machine was a one-off machine that ended up gracing the wages department of BMC at Longbridge. So a little bit of delay line revision. Mosaic had 3 types of delay lines: a single delay line, which was 1 word long, double delay line, which was 2 words long, and a long delay line, which was 16 words long. So the basic view is on the right of the delay line, you put in an electronic signal that is converted by the piezoelectric effect by a quartz crystal into an ultrasonic wave, which takes its time to go all the length of the tube to the other end, where it's picked up by another quartz crystal that transforms it back into a signal that goes through some regeneration circuitry, and you have your data circulating. If you want to read it, you read it from the circulation system, and if you want to input it, then you do it at the same place. What you can see from there is you have to wait for data to come round, and the address of a piece of data is in fact the delay line it's in plus the time slot that it passes through the regeneration equipment. And generally for a short delay line, it took a bit of data 40 clock ticks to get across, and that was called a minor cycle. And in a long delay line, it took 640, which is called a major cycle. So this is what the delay lines looked like. They were temperamental beasts. It took the post office a long time to get them going. Certainly, Wilkes got them going much more quickly, but he had help from our friend Gold and Renwick. What you had to do is, first of all, make sure that you compensated for changes in temperature. And you did that by utilizing long delay line 0 to send a fixed pattern through the system. And depending on how that propagated through the system, you would adjust the clock speed to keep pace. But the other thing you had to be very careful of is you had to keep all the delay lines at approximately the same temperature. And the way you did that was by building the apparatus you see in the slide, which is a big steel tank with the delay lines in boxes, insulated by ebonite chippings, and surrounded by a cavity wall. You also had to keep all the other electronics away from them. They were very temperamental beasts. So these machines followed the standard, well, at the highest level anyway, this standard von Neumann architecture, in that you had a control unit, an arithmetic unit, storage linked by some kind of bus structure, and all interacting with an input-output system. The diagram you can see is of the arithmetic unit, which had 3 components that could operate relatively independently. There was a multiplier, which took two 40-bit numbers and stored the result in one of the double registers as an 80-bit number, and that would run for 82 minor cycles. So you didn't want your machine lying fallow for 82 minor cycles, so you could go off and do other things while you were waiting for the result of that operation. There was an option to rotate a number right by up to 47 places. So that was in effect a multiplication. The most significant bit in Mosaic is on the right. You could actually pervert that to do a division for you as well, because of the way you used intermediate storage of the result. And finally, you had the function box, and the function box did everything else, which was 4 flavors of addition and 4 flavors of subtraction. You had the 4 flavors for different ways of handling the carry, and then logical operations of and, or, and logical or. So this is what the word looked like. It looks terribly cluttered, but you can think of it in 3 phases. First of all, at the bottom, the 4 function bits that say what you're going to do. Then 4 address fields, 3 7-bit numbers for the source and destination addresses, and 5 bits for the next instruction. And those would, in fact, you could get that next instruction from long lines 1 to 31. You couldn't use long line 0, so if you had 0 in that field, it referred to an instruction in short line 0. And then finally, it was a case of when you did what. And that was controlled by 3 more fields. There was the go bit, and the go bit is fairly crude. What it says is if the go bit's set, you go off and do whatever you have to do. If it's not set, then you're a wait instruction and you have to wait. Most of the things we'll deal with initially are go instructions. So then what you did was depended on the interpretation of the timing bit, and that was decided by the 2-bit characteristic. So this bit shows the control unit and how things worked. Your basic processing cycle was split into 2. A 1 minor cycle function called a setup beat, and then an obey beat that could take up to 16 minor cycles. On the last beat of an obey beat, you would look for that far right field in the instruction word, which is called next instruction or NIS, and you would read that into an internal short delay line, which you would internalize on the setup beat in solid, well, I call it solid state memory, but valve-based memory for reference throughout the obey cycle. During the obey cycle, the instruction would be obeyed, and then you would reach on the last cycle a decision. You would have this function called discriminate. Discriminate was how you managed to get a conditional branch. And you did that by, depending on the output, you would either pick up the instruction from the instruction from the memory location on the last beat or the beat after. And we'll talk about that in a little bit more detail a bit later. So this complicated diagram, I found I could actually explain more easily than there. We have on the right in the shaded area, the names of the 4 settings of the characteristics. The simplest of these is the immediate mode. And what the immediate mode says is until you decrement the up to and including 0, decrement the timing count, go away, do the operation and store the result. And on the last beat, get me the next instruction. And unless it's a discriminate beat when you get it from the location afterwards. The one at the bottom is a force discriminate, which means you just take the instruction after by default. Deferred is just like the immediate, except you only do the operation once, and that's when the timing count has been decremented to 0. And the final one we have is we can actually make the instruction cycle last the whole major cycle, but by setting the the timing count to the right value, then you could pick at which point in that cycle you actually did the arithmetic. Now, to look at how that functioned, it would be very painful if I did that using binary. So I'm going to do it using the nomenclature that RRE invented, which was quite simple. You start off by specifying in decimal your source 1 address, which in this case is long line 31, the function, which is an add. I'm going to add a number to short line 1, which is the second source, made it a go instruction, and I'm going to store the result in short line 1. It's an immediate instruction, so I'm going to do that 5 times. That's 1 plus the 4 there, and I'm going to pick up the next instruction from location 3. How that pans out when you put it in storage is like this. So there's the instruction, I've read it in, go through the setup cycle, and by the time I start doing it, I've gone this far down long line 31. And from this point onwards, we're treating the contents as an array, and we're going to add the elements of the array. And that goes on until we meet the final one with the timing count of 0, and we pick up our next instruction. Be useful to demonstrate this with an actual algorithm. We won't go into too much detail of it, but I've brought this up because it allows me to demonstrate quite what discrimination is. So this basic algorithm, I believe, was also used on Manchester Baby. And you pick a number and you want to find its highest factor. And you do that using 3 short registers, one for the number itself, a second one for a trial divisor, which you're going to vary, and a third for a remainder. And the name of the game is you adjust the trial divisor and do repeated subtraction until you get until you get a remainder of 0, which means you have a solution, you have a factor. And you apply a test to that remainder. Here I've specified all zeros as the source 2 address, and that is treated as a literal 0. And the destination address is this thing called D+. So D+ is an address which is off the range of the normal range of addressing. There are a range of fixed addresses that Mosaic use for this. And if the result was indeed greater than equal to 0, then discriminate was turned off. So we will pick up our next instruction, which is this one, which I'll explain in a few seconds. Or if it was off, we would pick up the one in the memory location after it, which is this one, which means we've got a negative result. So we've gone too far with our repetitive subtraction. So we adjust the trial divisor and go back around the loop. The D0 works in a similar method. Again, if the result is indeed 0, then we go to the next instruction, which tells us to record the number in short line 2. If not, we just go around the loop again. So it's one thing to lay this thing out sequentially, as Mosaic programmers would, but you had to plot out where everything went in memory. And this is that instruction laid out in memory, and this is the first discriminate instruction. Now what you can see is that's an immediate instruction, and it's going to pick between one of these two instructions depending on the state of the discrimination. We'll go down to the one where it's negative first, and what you see is that's at memory location 9. It's a deferred instruction with a timing count of 7. So we're going to look for our next instruction at 9 plus 2, which is 11, plus 7, 18, gone round the major cycle. We're going to subtract 1 from the trial divisor when we reach this point in the program, and then we will perform that instruction that's already there and carry on back down the loop. If on the other hand that had been 0, we actually do that check. That's again a deferred instruction, a deferred 9. We'll do that check at minus cycle 3, and if the result is indeed 0, we'll go off and tell the world rejoice, we have the factor. If it is not, then we go down to the instruction after that. It's a bit clunky, but it works. So having looked at how it worked, how do you get information in and out? Well, for output devices, you had 3. You had a card punch, an electric typewriter, an electric typewriter with an alternative character set. You could select which one of those you were going to use by carrying out an operation using a particular destination. The numbers had to be 101, 102, 103 respectively. And having selected that, you might want to clear an area of internal memory known as the output staticizer, which is this thing here, which would connect to the device you wanted. And you might actually want to reset that. So there was an instruction to do that. And then you just specified an operation with a destination 99, and it would take whatever was in the source memory and put that out to the device in question. Input is more interesting. There's an equivalent to the output staticizer called the input dynamicizer. It's called a dynamicizer because what it does is it takes a parallel pattern and feeds it serially into a delay line. That would be connected to the card reader, and it will make use of the fact that we can't do anything with long line 0. So if you specify a source of long line 0, it goes away and gets whatever is written in the input dynamicizer. In other words, the card image. What becomes even more interesting is what happens if you specify a destination of 0. Well, a destination of 0 means load whatever your input is into inst, which is the next instruction. This provides a means of bootstrapping the machine. So what you feed it is an instruction of all zeros. What that says is wait for a card and then read whatever is in that card and feed it as the next instruction. So what you might do for that first instruction is a simple instruction that will clear short register 0 so that it now has the 0th instruction in it. and execute that and then go off. And that again tells you to come and look at the input dynamicizer, which you might have a card which says read whatever's in the input dynamicizer and load it into a long line. So you've got a method of loading a program card by card. Now, there are more sophisticated ways of doing it, as Juice used with its triads, but that's the basic essence of it. One of the beauties of the Go bit was that it allowed you, rather than wait on the input from an operation, you could go away and do things in between reading different rows of a card. The useful thing you might want to do is take an output given in a decimal form and convert that to binary form, which was a method they used. So let's look at what this looked like when it got to RRE. That is the control room, which compared to most other things looks simple and well laid out. You've got a control desk of switches and lights, an electronic typewriter, not to be confused with a teletypewriter, a card reader and a card punch. You don't really get the sense of detail of what that console does for you. This is an emulator that I've written for the machine, which shows some of that. So I have a clear button, which will load the zeroth instruction for me. I have a stop instruction, which will convert every operation into a wait instruction, and a step instruction, which for the current instruction will override that. So immediately I've got a means of stepping through the logic of a program so I can test it. I have a button that allows me to read from the card reader. This lights button, which allows me, instead of displaying output to the card punch, to display it on the lights. But much more useful than that is this button called Instos. And what that will do is display the next instruction as you go along, so you can watch what your program's doing. Finally, down here, I have a set of 40 switches, which allows me to to program up an instruction directly, and a button to allow me to get that into the machine. And finally, a thing that RRE added, which is a breakpoint facility. So what I could say is, I want a breakpoint in this delay line, 5 bits, at this time cycle, 4 bits. So that was useful. This gives you an idea of the size of the machine they had. They had one room with all the electronics in, used a colossal amount of power, had many racks, lots and lots of cable, and a specialist floor. The floor in the second room, which held the delay lines, was even more specialist because that had to take 5 tons of weight. They had a third room for card punch equipment and a fourth room that held the control panel. This is a picture of what the racks looked like. You can see very big, and 12 of those beasts. So what did RRE have to do once the all-power transformer company that actually built the machine to the post office design turned up with it? Well, first of all, they had to make it available to other people in the civil service, so they had to have procedures for that. They had to get over teething problems. A couple of notable teething problems was, would you believe those pesky delay lines? They had to change the modulation method they used on them from using RF to DC. And another one was they were caught out by the hot summer of 1955. this day and age, it's hard to think of 1955 as being a hot summer. But it severely damaged the high stability resistors in the machine that made it erratic. So they had to improve the cooling system. There was always a way of managing subroutine linkage. What RRE had to do was formalize that so you could fit it within a hierarchical program structure. I think one of the nice things for me looking at this was you could see the impact the user organization had on the computer science behind this, in that they were doing things with a machine that would be picked up by others. It's worthwhile adding that in 1953, RRE and TRE were brought together to form a new RRE, which was radar for the whole area. RRE had been radar for the Army, and TRE had been radar for the Air Force. So they came together. TRE also had a machine, and the evidence is the two groups sparked off each other and learnt a lot from each other. The other things improved were the input routines. So the idea of being able to convert as you read things in and post-mortem things. An awful lot of the input they got was in the form of film, which had to be digitized. That led to the development of specialist film readers, of which more a bit later. They improved the console, so you've seen the breakpoint function they added. When they first got the machine, obviously they didn't really understand how it worked and had to fix problems as it came along. They started spotting patterns, understanding what was likely to fail when, and ultimately became more able to exercise preventative maintenance and improve uptime. And all the time they were working, they were developing new ways of doing things and building up a healthy library of subroutines that could be used across multiple projects. So how is it exploited? A kinetheodolite is an optical device that is used to allow a human to track a projectile going across the sky. And that recorded that path on film, which could be digitized, and that would give you a means of checking the accuracy of any radar equipment. And that led to this need for some kind of film reader. Now, the documentation for this is hazy, so a certain amount of what I say here is conjecture. But they did develop on a trailer a beast that had 2,000 valves in it and could take the film output and turn that into 3-inch 5-track paper tape. The inference is that would be taken back to one of those punch rooms and loaded and converted into punch card for installation on Mosaic. That could automatically be used to look at any errors in the radar equipment. They could use Doppler radar measurements to find out the relative speed of aircraft and therefore develop intercept strategies. They could address known problems. So the glint problem was a problem that led to inaccuracy in radar interpretation due to diffraction effects. They could look at tracking using 2 lots of radar, tracking an object across the sky, and feed that into their assessment of intercept strategies. They could use it for a number of design tasks, one of which was to improve aerial design. But they also used it to assess waveguard design, strategies for rocket propulsion, and then what might look like an odd one, tracking of solar eclipses. Now, it has to be said that before they joined TRE, many of its scientists had interests outside radar, one of which was astronomy. From the Army side, there was a chap called J.S. Hay, who would become one of the founding fathers of radio astronomy. And some guy called Bernard Lovell was at TRE. And funnily enough, he gravitated towards Manchester as well. Must be the weather. They also used it for autocorrelation analysis. They looked at improving telescopes as this trade-off with optical equipment, which they made a great deal of use of. And finally, they used it in analysis of satellite tracking data. That is useful in that you can spot mapping irregularities due to the variation in circumference of the Earth being fatter at the poles and so on, and provide improved mapping. Oops, I've gone the wrong way. So that more or less brings us to the end of the story with Mosaic. It was used right up until the early 60s when it was replaced by an altogether more powerful transistor-based machine called REAC. It did outlast TRIAC, but not by much. Pilotage on built is available from mid-1950 onwards. It does sterling work in looking at the comet crashes. It's picked up by English Electric as JUICE. And in 1954, the team start building Full Ace. It's delivered in 1958 and it soldiers on until 1967. Well, of course, by the time it was delivered, the technology underpinning it was already old hat. So that takes us pretty much through the Mosaic story and associated stories. Hopefully you've understood where it came from, who it was developed by, why, a little bit about how it worked, and a little bit about how it's used. So thanks very much for listening so patiently, and I'm happy to take any questions you might have.
Questions?
I hope to get rid of PowerPoint.
That should be all right. Can see me. All right. Question for Rowan Lim. Is your emulator generally available?
At the moment, no, it's not. I've been chatting to Dick about that a little bit. I guess what I need to do is learn a bit more about how BCS distributes these things and what sort of standard is expected. At the moment, the emulator was a device for me confirming I understood how the machine worked. It does have test facilities and things. I guess with a bit of work, it could be made available. It runs on a Raspberry Pi 4 and is written in C++.
If you want to see a mosaic today, where could you see one? Are there any existence in museums or whatever?
Well, there was only ever one of them, and unfortunately, you couldn't see it today. The nearest you could see would really be to look at what remains of pilotes, and I'm not quite sure if any juices are around.
Apologies if everyone else in the room knows this. Could you say a little bit about yourself and what brings you to this work?
Right. So,
Could you repeat the question so those online can hear?
so I'm asked where I come from and what brought me to this work. So I started out as a physical chemist, meandered into computer programming on DEC PDP-11s and data communications, and found myself working for BT. So I've done quite a bit of work on BT's past with packet switching, and it's probably important to say that one of the guys who programmed both Pilot ACE and Full ACE was a chap called Donald Davis, who introduced the idea of packet switching to the post office, and ultimately sent one of his acolytes, Roger Scantlebury, across to a conference at Gatlinburg, where he introduced the concept to a chap called Larry Roberts, who had a minor American network called the ARPANET to deal with. So basically, having done a fair bit of work on packet switching, I was looking around for something else interesting to look at. I came across Mosaic and felt the need to re-engage with my programmer roots and take a look at it.
Thank you. Owen? Does any original Mosaic software exist? And the reason I'm asking that is because you said you wrote the emulator to verify you understood the machine, but without original software, you can't be certain. So
fragments, yes. So one of the things, most of the original source material came from BT archives and through the Alan Turing archive. But I discovered that at Malvern they have a group called MRAFs. And MRAFs were able to supply me with the programming manual that had a significant number of fragments of code in. So in fact, a number of the 100 or so test routines I've got come from that. They also come from Coombs's, where he gives two algorithms, one the one I've showed you, and the other one is one to calculate the sine and cosine of a number. And that gets you thinking a little bit like the programmers did, because you start having to think about fixed point arithmetic. And you start having to think about scaling numbers up and scaling them down. And this is where you discover that stop thinking in terms of 100 and writing a divisor. Why not scale in terms of powers of 2, like 128, and use the variable delay to scale up and down? And that was considerably quicker. Sorry, your question.
Did they have a dedicated team of programmers, or were the scientists doing the programming themselves?
I think it was largely.
Repeat the question.
Sorry, I'm asked, did they have a dedicated team of programmers, or were the scientists doing the programming themselves? It was largely the scientists doing the programming themselves. They did have some teams that would do the data entry for them, so punch the cards.
Dick?
Yes.
To go back on a previous question, although obviously ACE and use and its progeny and Mosaic no longer exists, there are a couple of Bendix T15s still in existence, one of which has recently been brought back into working order. Sadly, they are in America.
Yes, and I'm not sure we ever got any of them over here, but yeah.
Was any of the work performed on Mosaic classified, do you know?
It almost certainly would have been.
The question is, was any work classified?
Yes, so the work, so the actual programming work would have been classified because it would have reflected secret radar. The actual description of the machine clearly was not, because first of all, Coombs published 5 papers in the Post Office Engineering Journal and actually described the machine at several conferences, including the ones that everyone was at in Manchester, Cambridge and at NPL. Also, there are full research reports that were available from Post Office archives and are also available on the at the Alan Turing Institute. But actual programs that did real stuff, I would imagine, is classified.
Any more questions?
Nothing online.
Any questions online?
How reliable was it? I mean, with the very complex timing mechanisms, and you've got valves and very temperature dependent delay lines, how reliable was it in practice? Mean time between fails.
I don't have the numbers off the top of my head. They're actually in the paper I wrote in the International Journal of the History of Engineering and Technology. But it was quite, it's one of those things, when it worked well. When it didn't, it didn't. I think once they got over the issues with the temperature variation and the nature of the modulation on the delay lines, I think it was very reliable.
Question online, how many delay lines did it have?
Right, 28 short, 3 rising to 4 double, and depending on whether you count delay line 0 or not, 63 or 64 long lines.
What do you mean rising to?
RRE put in an extra one.
Any more? Well, that was fascinating. Thank you very much.
Thank you.
I think we're all now in a position to go off and program it.
So I better get on with the emulator.
Yeah. Well, thank you very much, Edward. That was a real eye-opener. Thank you for coming, ladies and gentlemen. Can I advertise the next meeting, which is on 19th of February, when Gareth Edwards will be talking about IBM versus Compaq, which should be a nice tussle. Thank you very much.
Yeah.